Okay, so hi folks, welcome to Remars again. I know that you've had an exciting time, hopefully so far. My name is Mbanga. I lead business development at Amazon Web Services for our machine learning platforms and services. So if you heard of Amazon SageMaker, it's one of my babies in the data science ecosystem of Amazon Web Services. And what I do with my colleagues is to work with our customers to make sure that they achieve success with our machine learning technologies, whatever success means for them. So we're a team of technical people. My background is in physics. And today, I'm joined by Adam, who is going to have the opportunity to share what he's done using our machine learning platforms on SageMaker. Adam, you want to quickly introduce yourself?
Yeah, I'm Adam Sullivan. I'm from Change Healthcare. And Dan's going to talk a little bit through some of the stuff on AWS, and then kind of tag team, and I'll talk a little bit more about our company and how we're actually using AWS to do some really crazy stuff in healthcare. So,
all right.
Thanks.
Thank you, Adam. Okay, so let's get started. Let's jump right into it. Who here is familiar with AI? Everyone, of course, everyone. Super exciting. We are at an AI and robotics conference, and then the way I like to, get this conversation started is always by having a frame of reference. And I know you're familiar with all of these, but the reason I'm putting that up is basically to share some of the insights and the way as well that strategically we're looking at making sure that AI is available for every developers and data scientists in the world out there. As you all know, it's a fairly fast-moving ecosystem. And then the way I like to categorize that is kind of wrap AI in a combination of hardware and learning algorithms, especially in the world of deep reinforcement learning nowadays and robotics. And the idea behind that is to achieve the kind of tasks that the human would achieve with the machine, essentially, right? And then to kind of power that from a mathematical and statistical standpoint, machine learning comes in with a set of algorithms and statistical models and all the maths behind the pattern finding. And you can break machine learning in a few different types of domains, but where we're focusing mostly at AWS in the way that we package the technology for our customers, developers and data scientists and all builders to use is by basically making available the traditional machine learning algorithms first, but also we're making significant investments in deep learning, for example, which is basically a mechanism to fit a neural network structure to the data set that you have. And in reinforcement learning as well, which is very significant in the world of robotics. So essentially, strategically at AWS, we make sure that we have most of these areas of AI covered. And basically what we do is that we fund teams of engineers and scientists and software development people to package these capabilities into containers, into algorithms improvement, into GPU capable technologies, and make sure that it works well for the builders. So the idea, the intent behind our strategy is to make sure that you as a developer and a data scientist, instead of starting at point 0 to point 100 in your development, you start at point 60 or 70 to point 100, and all the background work is done by us. George Box said that all machine learning models are wrong, but some are useful. I really like this quote because our intent is not particularly to solve the machine learning or the overall intelligence problem for you, but there are many useful applications of machine learning today for the enterprise world. There is a decent amount of research, and what I'm passionate about in this world of AI is the fact that you can actually join these two ecosystems now in a seamless manner, using Python, for example, in the research ecosystem, and the enterprise is adopting Python as well. So what we do is to make sure that we extract as much insights in the research world as possible, but we think about it from a practical, useful standpoint. So what you see is that most of the things that we do is actually to build machine learning models that are really driving business outcomes. And then Adam is going to share some of that work with you today. And the way that I like to categorize these machine learning outcomes or business outcomes capabilities is in 7 key goals, essentially. So either you want to reason on top of your data, or you want to explain the dynamics of your data by inferring a certain function that describes your data, or you want to design a certain problem. In the world of physics, for example, force is equal to mass and acceleration. That's a design that you can have, and a machine learning model can also give you a design that represents your data from that perspective. Or you want to communicate some results to your team. You can use the machine learning models that can help you explain the behavior of certain data sets or certain users or consumers or customers or certain artifacts that you work with. The other family of activities in terms of business outcomes that we see some of our customers focusing on is the actual part of acting on top of the insights. So there's this descriptive aspect or the data science aspect, like we like putting it, and there's the machine learning aspect where you're actually building a piece of software that you're putting into some kind of end-to-end machine learning pipeline. And the type of actions there or the type of goals there that we observe are things like acting on top of some insights or running some predictions for seeing into the future, essentially, or exploring a certain environment, physics environment, for example, using a simulator and applying machine learning on top of that. So the way we're thinking about it is in two major categories. One is a data science category, where essentially you're building machine learning models for the purpose of basically making a business decision. And the second one is the machine learning category, and I actually got this from Andrew Ng, where you're building end-to-end machine learning pipeline, essentially software. And when you think about building machine learning pipeline and or software, the challenge there is very, very significant because you're not just thinking about the data science aspects as in the TensorFlow, the PyTorch, scikit-learn, and all that, but you're also thinking about continuous integration, continuous delivery, software updates, and all the software engineering practices that you have to put together with the data science practices that make that work. And of course, the business goals drive the type of data that you need to acquire, and then that drives the type of algorithms that you can use, and that drives the type of models that you can use, and eventually the models gives you the business goals again, and the flywheel continues. So this is kind of how strategically we're looking at it. And what we're observing is that, again, there are two major transitions in the world of machine learning today. Some folks are moving from the age of discovery to the age of implementation, essentially, where in discovery, well, you needed to have a lot of people with PhDs in data science and machine learning, a lot of folks were doing research and development, but now machine learning is getting in the hands of basically every developer. You don't really need to have a strong or deep experience in the computer science ML domain in order to take advantage of machine learning. So what we do is to try and make sure that we package the intelligence of the mathematics and the statistical models enough for people that don't have as much science experience to still take advantage of implementing machine learning capabilities. And the second trend that we're observing is a movement from the age of expertise, meaning that there was a need for a lot of experts, to the age of data, where you can be an engineer or good enough Python person with enough data. Your model is going to be better than the PhD that doesn't have as much data as you have. So our mission at AWS is essentially put machine learning in the hands of every developers and data scientists. And we're very serious about it for the reasons that I called out before. We have an R&D hands, an R&D department. We have an algorithms and a science team that is basically improving the standards of the machine learning algorithms that exist out there. But what we really come out with is the practical packaging and implementation of these machine learning algorithms. And that looks like this. And I'm pretty sure you might have seen this before. This is our machine learning stack. It's basically a 3-layer stack where at the bottom of a layer, we do package or invest in making sure that we have TensorFlow, MXNet, PyTorch, Keras, and all the deep learning libraries available and configured and working well with GPUs and all the other infrastructure that the AWS cloud provides. But somewhere in between the bottom of the layer, and by the way, the bottom of the layer is fully available. You can pick up the frameworks and run them on Amazon EC2. It's basically designed for the people that know what they're doing. They can dig into TensorFlow and write their own TensorFlow code, and then come up with their own machine learning models, leveraging the improvements that we've done there. In the middle of the layer, that's where we're building orchestration, continuous integration, continuous delivery. That's where we're really building a marriage between the data science and the engineering capabilities that we have at AWS. So we build technology like SageMaker Ground Truth, which is basically the entry point for any data science or most of the data science problems that you have out here. You probably need to label the data that you have to work with. So with SageMaker Ground Truth, we make it possible for our customers to basically send their data sets to either a 500,000 plus workforce that is out there in the public, or a private workforce that basically could be their own staff or some people that are their friends or whatnot, or a third-party workforce of data labelers that would provide you with SLAs and other things like that. So ground truth is really our mechanism for automating the process of getting labels to the data that would eventually help our customers essentially build machine learning models. And I'm going to go faster through the rest of the capabilities here because I want to believe that you're familiar with. Who here is familiar with Jupyter Notebooks? Pretty much everyone. So I'm not going to bore you with that. So we have Jupyter Notebooks available. We also package machine learning algorithms, and we have a marketplace now that has an extensive list of algorithms that are built by our customers, and we make it possible for buyers and sellers to connect and basically have a trade through which we control quality and intellectual property and stuff like that. We also make significant investments in reinforcement learning. I'm going to talk a little more about that towards the end of this conversation. Model optimization, hyperparameter tuning. Basically, what we try to do here is package these capabilities behind APIs and make it possible for our customers to just summon these capabilities and have them launched and for them to basically train their machine learning models in a short period of time as opposed to having to do that for many hours or days in the past. So we take care of the undifferentiated heavy lifting, and our customers can focus on the machine learning part. And at the top of the services, we basically have pre-trained machine learning models that our customers can use for vision, speech, language, and all that. Okay. But then it all starts with the data. Usually, you want to have your machine learning model crunching your data. And for that, you need a data lake strategy. So to have your data lake strategy, the way we're looking at it is Amazon S3 is that landing zone that is infinitely scalable, where our customers dump terabytes and terabytes of data, and it has ETL capabilities in the form of AWS Glue. And with that lifecycle, we can build technologies on top of that. But strategically, what we're doing at Amazon is to make sure that every team that is building data analytics or machine learning services speaks natively to the data lake capabilities so that it's fully integrated. So for business intelligence, for example, we have Amazon QuickSight. For ad hoc query, we have Amazon Athena. For analytics with Spark and the Hadoop ecosystem, we have Amazon EMR. And for data warehousing, we have Amazon Redshift with Redshift Spectrum. And for machine learning, we have Amazon SageMaker plus the AI services. Now, my call out with this slide is to essentially show you the arrows that keep going up and down between the analytics and machine learning services and the data lake. So they are natively integrated so that you can have one single source of truth, one ultimate copy of your data set on Amazon S3. You have your data lake ETL capabilities that are crunching the data, but every other tool that utilizes the data from a data analytics perspective or machine learning perspective can natively talk to that data lake. So that's how we're building strategically. Now, the second trend, or the second thing that is important, digging a little bit into the machine learning capabilities, is that what we're trying to do is to enable what we call AI-driven development with Amazon SageMaker. So again, Amazon SageMaker is our end-to-end machine learning platform that basically enables our customers to label, build, train, tune, and deploy machine learning models at scale. So I'm going to dig a little bit into SageMaker so that you get a feel of it. Well, initially, you start with essentially, the developers, or again, if you're building a machine learning model that has to live in production, then you're probably using a software development kit. Or if you're using a camera or a robot or anything like that, that's basically a client to the SageMaker ecosystem, depending on whether you're training or running some inferences. But who are the top players in Amazon SageMaker? And by the way, who here is familiar with Amazon SageMaker? Okay, about 40%. So the top players, and the way we basically design SageMaker looks like this. It's an end-to-end machine learning platform that has 3 or 4 major capabilities. The main environment for developers to basically write their data science code in SciPy, NumPy, Matplotlib, Scikit-learn. The main environment where people play with these capabilities is Jupyter. So we make Jupyter Notebooks available. We also have a second major capability that is for data labeling and data training and data tuning. And we have a third major capability that's for model hosting or model deployment when the models are ready. But really, what I wanted to show you today is not these SageMaker capabilities, because you can read them online. Again, the key, the macro message that I have here is the integration between the machine learning capabilities and the rest of the ecosystem at AWS. So you can see that from a control standpoint, there are other technologies that are fully integrated with Amazon SageMaker, like AWS Identity and Access Management, or the SageMaker role from AWS as Identity and Access Management. That makes it possible for you as a user to really, from a granular standpoint, control who has access to what in this machine learning ecosystem. The second key and important sister feature of SageMaker is the whole security ecosystem. So we want to make sure that not only machine learning is usable on the cloud, but it is secure. So we've integrated SageMaker with Amazon KMS, which is our key management service. That makes it possible for our customers to use their own encryption keys and encrypt data at rest, encrypt data in transit. And basically what we take care of is building the entire integration and make sure that the plumbing is taken care of so that you just specify your key and we take care of the rest. And the third major sister or brother services that exist around SageMaker is the other services that are used for serving inferences. Because SageMaker makes it possible for customers to have an inference, what we call an inference endpoint. And from the endpoint, you can plug an application, a third-party application or client application, that could be a robot, that could be a web app, to the ecosystem. So for that, we use technologies like AWS Lambda, Amazon API Gateway, and I think Adam is going to talk a little bit about that. And of course, the data lake lives in Amazon S3, and we use Amazon ECR, which is our container registry, to store what we call the algorithms. And the algorithms in SageMaker can have multiple forms. You can use a PyTorch, TensorFlow, MXNet, or any other deep learning container that we make available. Basically get it started and then train your machine learning model. Or you can bring your own algorithm, or you can use what we call Amazon-provided algorithms. These are about 17 algorithms, some of them coming from Amazon.com. Many are very common open source algorithms, and then you can grab them and plug your data into it and then basically run your models. Let's dig a little bit into the ecosystem there. So from a notebook standpoint, basically what we do is that we automate the process of launching a machine that comes pre-configured with the popular machine learning libraries, things like, again, Python, NumPy, SciPy, Matplotlib, and all the things that are related. And it's attached to a disk. And again, the disk could be encrypted with your keys and all these other things. But the other very important thing that we do there is to make available hundreds of machine learning examples, end-to-end examples, within that Jupyter Notebooks ecosystem so that you can get started solving your problems rapidly. And I cannot tell you how many examples or how many cases I've seen where our customers just look at our example, look at how we solve a problem. Many of them are written by our scientists, and then take the sample data out, plug their own data in, and solve their own problem. And then from a model training standpoint, we basically launch and orchestrate the launch of a cluster with the possibility of streaming data from Amazon S3 directly into the cluster. Again, that's C++ code that we wrote in the back end to make sure that that is possible. And then the cluster can come up and train your machine learning model at scale. So if you're launching a TensorFlow ecosystem, we know how to scale that. If you're launching a PyTorch ecosystem, we know how to scale that. And to dig slightly deeper into what one of these Docker containers that we use there looks like, we basically have within this container a data agent and a log agent. The responsibility of the data agent is to do the log aggregation. If you've ever managed your own cluster for machine learning or deep learning, you know how challenging it is to find the logs for multiple machines. So we basically take care of that. And the data agent is responsible for going to Amazon S3 and fetching the data and intelligently understand how to shard the data and distribute the data to multiple machines that are contributing into the cluster. So again, there's a decent amount of cluster management, cluster launch, cluster orchestration that happens there. And as you go up the stack within the Docker containers that we provide, we have data distribution or model distribution libraries depending on the deep learning or machine learning framework that you use. We also have CUDA for GPU support. And in this example, I have PyTorch, but you can flip that with TensorFlow and other things. And we do have a very powerful Amazon SageMaker SDK, which basically orchestrates the process of launching this entire ecosystem rapidly. And on top of that, you have your algorithm. So basically, the algorithm can be your algorithm, and again, one of the Amazon-provided algorithm, but everything that comes below that stack is taken care of by us. And from a model hosting standpoint, SageMaker provides an endpoint that can basically do auto-scaling of the inference capability of your machine learning model. So by starting an endpoint, you can send real-time inference requests to the endpoint, and we'll be able to serve that at scale using API Gateway and Lambda. And then if you are also interested in batch transformations, then SageMaker can also provide batch transformations. So I hope this was useful, the general architecture of Amazon SageMaker, the internals of it. And now I'm going to hand it over to Adam to, and yeah, essentially that's a little more about the control and the flow. Now I'm going to hand over to Adam to speak about their implementation of this entire ecosystem at Change Healthcare.
Thank you. Thank you. I'm Adam Sullivan, and I'm very thrilled that Amazon invited me here. Jeff Bezos warmed up for me, so thank you all for being here. It's a good way to look at it, right? Thank you all for being here, though. I know that it's late in the day, and there's been so much coming in, and I'm going to talk a little bit today about Change Healthcare and what we're doing with AI. And it's the past few years we've heard so much about what AI can do, and theory exercises of different things of we can try this and try that, and we're actively doing things and making an impact within our company. So that's my goal today, is to share some of those what's going on within Change Healthcare. So at a high level, I just want to give you a little brief, who we are, what we're doing, a little bit of some of our actual applications, and I have a demo of some of the things we're doing with SageMaker, so you can kind of get a feel for it. I'll give you a little bit under the hood of how we're actually doing this with our integration patterns within AWS, and finally any closing thoughts that we have. So who we are. Who's been to the doctors twice in their life? Anybody? I thought so. So Change Healthcare, we are kind of one of the largest players in the healthcare system that a lot of people haven't heard about. And the fact of the matter is 2/3 of the US healthcare system flows through Change Healthcare. On one side, you've got hospitals and doctors that are performing services. You've got insurance companies over here that need to insure people and reimburse for those costs. And then, you've got the patients. And you need to connect all of those. And Change Healthcare is the network that drives a big part of the US healthcare system. Whenever you go to the doctor, they say, oh, I think you've got the flu. They're going to code a claim. Maybe they've done a test on you. They will codify that as a claim. That claim will get sent over to the insurer, who will look at it, think about it, sometimes scratch their heads, sometimes deny the claim. Anybody ever had a denied claim where you're just like, who's paying this? And then obviously the patient has to settle at the end. And the fact of the matter is, if tomorrow Change Healthcare ceased to be a company, the U.S. healthcare system would come to a halt. There's no way for hospitals and physicians and insurers to be able to communicate without a centralized network. So we've, 2/3 the U.S. healthcare system, 900,000 physicians we connect, 2,200 payers, dentists, pharmacy, labs, you name it, it's coming through Change Healthcare. And we don't just stop at kind of these network connections. We also do things like helping hospitals to optimize their revenue, helping payers to fight and find fraud, waste, and abuse, and helping patients kind of navigate some of the difficult pieces of the U.S. healthcare system. So in a nutshell, that's who we are. There's a lot more to it. That's the best I can do if I only have 30 seconds. But huge is the big piece that's important to take away there. So given that we've got this integration into the U.S. healthcare system, we don't have radiology exams, we don't have imaging studies, we don't have all the really cool things that are happening in healthcare right now in the AI space. So if you came here for that, I apologize. But what we do have is we've got more data on the U.S. healthcare system than perhaps anybody. And we've got the way to get into our, if you're a physician, your number one pain points aren't necessarily how do I find the best, how do I try to identify different cancers in a imaging study. They think that they have a good grip on those types of tasks. What they do have is they have back offices full of nurses and staff that are working through claims, calling people on the phone, filing faxes between the payers and providers to get paid, essentially. And a lot of the new work with the electronic medical records, there's a lot of typing that goes on. There's a lot of administrative overhead. So the entry point into the U.S. healthcare system for AI is reducing that burden and helping the U.S. healthcare system free itself from this 10% of every administrative dollar being spent on administrative overhead. That's we believe that's our where we're going with our AI journey within our company. What we really like to start to talk about, though, is that the U.S. healthcare system has a large problem. I talked about the denials problem earlier. $3 trillion in claims submitted through the United States. $262 billion are outright denied. And that's $4.9 million per hospital. And a lot of times it's very simple things that need to be fixed or addressed. But a denied claim means that a service was performed and somebody is not getting paid for it. And the problem is, the problem is across, it hurts everybody, payers, providers, and patients. The payers don't want to have to deny a bunch of claims. They don't want services being performed that aren't permitted. And so we've got, within the U.S. healthcare system, this is a massive problem. And if you're a hospital in Clarksville, Tennessee, do you have an AI team sitting at your beck and call to be able to try to solve some of these problems? And so that's how we're trying to think about how can we liberate all this data we have, provide it back to our customers in a way that we can enact meaningful change, change healthcare. So for us, though, we do like to think about our team, and we generally, I know this probably isn't much of a surprise to anybody, but for any good AI endeavor to take place, you need a few things. You need data, usually lots of data. We've got that covered, believe me. You need to have an install base and an embedding in the workflow. You need to have a way, and this is where it's hard for a lot of startups because maybe they have data and talent, but how are they going to get their solution or product back into the marketplace? And if our integrations with our customers, we have a pretty massive install base. And you need talent and infrastructure. And so for us, we've got a team of 50 data scientists in the Bay Area that we've got a really awesome team that has developed some really cool stuff over the past 3 years. But for us in healthcare, one of the big things that whenever we see different breaches that are reported, those are legally required to be reported. A breach of somebody's personal health information is required to be reported on. And so the mere idea for a lot of people of placing data, health information in the cloud is a very scary proposition. But we've nailed that piece, and we've done that through a whole bunch of certifications, a really awesome InfoSec team, and a lot of controls in place, and frankly, a lot of the partnerships with AWS to be able to enable that partnership with our PHI. So for us, though, what we've been actually tackling on, getting into a little bit of the meat of the bones of what we're actually trying to do. Or no, what we're actively doing. We have developed a pretty strong deep learning capability because of our need to understand medical records. And we're not talking about kind of Epic and Cerner integrations and all the EMRs that everybody knows about. Most of our medical records come in PDFs or even scans or fax machines. So, step one out of the gate, we've got a mess of spaghetti of OCRing that we need to do. Once we get through that, though, we're able to actually identify and say, we've got people that read medical records or charts or contracts or whatever it is in our company all day long, And as an example, if you're trying to find fraud, waste, and abuse, if you get a chart that has no fraud, waste, and abuse in it, and you can identify that up front, having a human take a look at that is a waste of their time. And so we're able to do things by reading and understanding medical records to look for the same things that our humans are looking for, to be able to change some of our workflows within our company. We talk, and that goes into language understanding and deep learning. If anybody knows about how we actually think about medical codes, there are tens of thousands of what are called procedure codes, and those can be a knee replacement or an office visit or a physical therapy visit or whatever it might be. There's also tens of thousands of diagnoses. Injury, and it gets pretty specific, injury of the left finger on the top, as an example. So the combinatorics of a claim are massive. Payers and providers have very concrete contracts on how they reimburse each other and define the rules of the game. And we've been able to, in a way, using deep learning, be able to reverse engineer some of those capabilities of why are these types of things being denied? Why are these claims being paid? And we do think that some of our ability to understand these relationships between procedure codes, diagnosis codes, payers, providers, and those types of things are essential. And then the last piece that we really have mastered, frankly, is active learning. And for us, there's a few instances of this. Not every label is correct if you have a supervised data set problem that you're trying to solve. And secondarily, not everything is actually labeled. And so whenever you're staring at a problem, how do you actually go and solve it? And for us, one of the big ways is, well, we're going to go find the label and create the label as part of the task. And so, the example I gave of fraud, waste, and abuse earlier, maybe we don't know what the human was actually looking for, but we can tee those up to experts to learn what it is they're actually looking for and create models kind of on the fly as people are doing their work. So these are kind of our core tenets and capabilities of what we've developed. But in terms of value, I gave the example of the natural language understanding problem. If we can, it's not as simple as let's just highlight the sections of text so that we can feed those into some visual or something like that. For us, we are trying to, and we are actively changing our workflow to say, there is no fraud, waste, and abuse in this medical record. We don't need to take a look at it. And we've already done it using some of our tools. If you're reviewing thousands and thousands of records or contracts or whatever it might be, your ability to change your success rate matters significantly. And so those are the types of ways that we're delivering value on our natural language understanding. I say this a lot, but in healthcare, a lot of our problems are very low-hanging fruit. Healthcare is so complicated and messy that usually, I was telling Dan earlier that a lot of times we build deep learning models for fun because we should have just stopped at a logistic regression because it's probably going to solve all of our problems. But on this, this kind of second example, if you're operating a call center where you're trying to identify members who are eligible for Medicare and Medicaid, the simplest of models can identify to say, let's prioritize who we're actually attempting to call and outreach to, because if they're just not eligible because of a mechanical issue, they don't check all the boxes. Let's stop calling those. Let's stop trying to outreach to people that aren't going to be eligible. So I know this sounds like the world's simplest problem, and everyone's like, yeah, no, duh. But it emphasizes how much we can tackle some of these low-hanging fruit problems with models very quickly and reactively within our domain. And our last example is on the claims lifecycle AI capability that we announced. There is a press release about this. We announced it back in February or March or so. But I gave the example of the claims being denied. And what we did was we, it's powered by SageMaker, but we've been able to identify that, if you've just coded up a claim and it is going to be denied, the action that most people need to take is they need to actually go through and fix the claim so that they can actually get it reimbursed. And so what we're able to do is identify at the point of submission about 35% of claims that are bound to be denied, flag those, and provide the guidance back to the operator to say, hey, you need to fix this before it actually goes out. And that represents within our company, within our customer base, $6.2 billion in forecasted allowed amounts that we can flag at the point of submission, and hundreds of millions of dollars of people spending their time calling and faxing and doing whatever else within our the customers that we have. So these are real. These aren't theory exercises. These are things that we've delivered value on back to within our company. So I want to just show that last example on the claims lifecycle piece. I want to just show you a little bit more about what I'm talking about. And so this is an example of and this is purely a mock-up. This isn't a product or a solution or anything. But this is a fake claim that we've created. This is after you leave the doctor's office and you go home, somebody has to go in and type all this information in to a form that is going to be submitted to indicate what's happened to you. So they have to give the insurance information and who they're, a few different identifiers and those types of things. And what we've done is basically, the actual workflow would be that you've coded this and then you hit submit. But to demonstrate, we're like, before you do that, let's just get some advice about what's actually going to happen to this. And so this is hitting a real SageMaker endpoint that I'll show an example of in just a second. But the miracles of live demos. This one will work, pretty sure. Hold our fingers. Oh no. Well, what actually populates there, what populated there 20 minutes ago before I showed up here, is to basically say, hey, this thing is going to be denied, and we think the reason is because of this. You need to go in and fix this particular element of the claim to say, hey, this is, we've got an error there. So, and actually we've got it mocked up here for the example, and you can see that, you get the advice saying that, hey, this is going to be denied for a particular reason that some hospital staff would understand, and we can give things like, how much are you going to be reimbursed? How long is it going to take you to get paid? Key drivers of what people refer to as kind of protecting their AR, which is their claims going out the door and their reimbursements coming back in. So just as a high level, that's our example. So I do want to talk a little bit about how we do this, and what's important to kind of identify is how we're actually leveraging AWS to do this work. And so this isn't theory. This is what that site is actually doing. But the overarching theme is that we have built up. And I have another slide that I like to share of how many people it actually takes to build this. If you're doing it on your own, and if you're letting AWS do the work, it's only 2 people that are actually doing anything here. But what we've done is that we've enabled our data scientists to build out the models that they need using the tooling that they need to get the job done. In this case, we're using TensorFlow-based models for the ability to understand claims. And we're training and doing that work in SageMaker itself. So our data scientists are spending their time over there. We're putting bounds around them so that they are able to work in notebooks or in code, whichever they prefer, and leveraging SageMaker for training, as well as testing some of their inference capabilities. They are able to get access to data because we've actually built out a pretty good data lake strategy. And so all of our data goes into a giant data lake. Data scientists can go in and pull out whatever they need, whatever they want. We're using AWS Glue to catalog some of that data so we can know where it lives at any given point and fire that. That's all based off of S3. And our data scientists are able to pull that into SageMaker seamlessly without having to call up a data engineer or do whatever else they need to do. Once they have a model that works, we have a CI/CD pipeline that will pick that up, fit it into Artifactory so that we can track those models and catalog them and know what their versions are and those types of things. And those go to scoring endpoints within SageMaker. And so that's kind of our top right there. Whenever the application in the example that I showed earlier, we've got a consumer that's sitting on an application of wherever it might be in the world. That's one of the great things about what we've done with AWS is that we're able to expose our HIPAA-compliant services to anybody that we need to. And those customers use the application. That's using the Amazon API gateway. We've got some Lambda functions sitting in there we don't just have one model, we actually have a handful of models that we're using at inference time, so we can kind of pick and choose what we need. And so those Lambda functions are firing those payloads off to the SageMaker endpoints, scoring and sending everything back in a nice, complete story of what they're trying to do. So for us, this has been a winning pattern. Whenever we had started, 3 years ago, and we were doing a lot of Spark-based modeling, a lot of homegrown, home-built type of things, and I can remember, sitting down and typing out loads of JSON to try to get everything to actually be able to deploy into production, and we've basically by using some of the tools that SageMaker has built out, a lot of our deployment patterns have gone down to weeks and even to days. That from model time to actually delivering value can be very rapid. And if somebody trains a new model and we've got some update, we fire it through this process and we're able to get a new model deployed in a matter of minutes. And if anyone knows anything about healthcare, 1, minutes matter, but 2, they're not really respected. And so our ability to be able to move very quickly is, it's a major win for us that we're able to take advantage of. So for us, this has been a winning pattern. And you're welcome to take pictures of it and whatever else. There's no secret sauce to it, but it's been great. So so with that, I do want to thank everybody. I know that Dan has some closing thoughts and remarks, but like I said, where we sit in the healthcare system, it's not going to be the prettiest and sexiest AI applications that everybody wants to talk about, but it is going to deliver value and impact, and it is delivering value and impact. We're trying to change those things where, why am I getting a denied claim? Why are hospitals having nurses sitting in the back room and not, with their patients delivering care? So at the end of the day, we do think that everybody wins. We don't think there's a losing proposition to the work that we're doing and how we're trying to leverage AI. So thank you all very much.
Before you go, you shared a lot about the problem statement, the technology, the architecture, and then there's some great work done there. I like what you said when you said that in the back end you don't have just one model, you have multiple models. So you have like a business rule or a Lambda layer that has some logic that decides how many models you want to tap into, so that at the end of the day you kind of provide value to the end user. So that's all great, but it assumes that you already know the problem you're working on. Can you say a little bit about how the team organizes itself on problem analysis? How do you go from the problem to actually building models? What's your process there?
No, that's a good question. For us, there's a few prerequisites before you can kind of even get started. One, you need to have data. We talked about that. You need to respect the data that you have as well, and so we need to, legally be able to, legally and ethically be able to work with that data to deliver impact back to our customers.
That requires a lot of encryption, access control.
Entirely. And then obviously to be able to leverage anything with AWS, that feeds into that. But for us, we don't have generally data scientists that will sit and churn on models. We want them integrated into the product lifecycle at every step along the way. And so we don't have people that are off just building pipelines or just building models or whatever it might be. They are right there in the product development workflow.
Right.
And that iteration cycle is direct with that. And so we work in kind of weekly iterations. It's not really a Scrum process because data science is very exploratory, and a lot of times you are discovering new things along the way. But for us, the ability to take what we're doing and then leverage it into AWS, we want to take a lot of those things we're spending a lot of time on and get them back into the product development cycle. So
thanks, Adam.
Yeah, thank you.
All right, exciting stuff. So what's next? We spoke about the data platform. We spoke about the importance of data, machine learning, the paradigms there. You've seen an application. I'd like to talk slightly about what's next now, especially because we are at robotics/machine learning conference. So I have some thoughts about the future. And I packaged that in the third category that I want to talk about, which is from big data to big estimation and control. So if you ever deal with reinforcement learning, it basically tries to address the scenarios where, taking a step back, if you're dealing with supervised learning or unsupervised learning, the assumption there is that you have the data. The assumption is that the data is somewhere, then you have to load that somewhere, and then train a machine learning model and come up with your insights. But what if you don't have the data? What if you're getting the data as you're using the system? Example in real life robotic experiences where you actually have to explore in order to discover. Or what if your problem has to do with a physical or physics environment that has so much variability that you wouldn't particularly have as much data as possible before you train the model at rest. That's kind of the opportunity space for reinforcement learning. So what we're seeing is this paradigm shift from learning from big data or data that is already cataloged to actually learning from experiences. And within the experiences world, you have the estimation, which is basically the estimation of either where you are, if you're working on positional problems, or the estimation of your reward or your maximum reward function if you're dealing with a reinforcement learning problem. And control is also very important because many applications, if you have attended a talk about Amazon RoboMaker, for example, there's this big approach towards using things like the robotic operating system and Gazebo, an entire simulator to simulate the real world, and then bring that back to the real world. And when you're doing that, control is important because you want to act in the real world, so you want to send the kind of answer of the brain or the model into some artifact that actually has actuators that can control the behavior of this utility or this model in the real world. And you can bring that back to practical use cases like changing the temperature of the HVAC system here in this room depending on the behaviors of the people that walk in and out and stuff like that. So there are many applications, and we're seeing that as a big paradigm nowadays. And just to show some experiences or some examples in reinforcement learning, again, this is aligned with the fact that you don't particularly have the entire data set, but you're working off of a physical environment that has to learn or that has to estimate the data as it's using the system in real life, in real world. And perturbation can happen in that world. What would you do if that happened, right? So that's an example. That's an experiment that was done at OpenAI. And another example is this tiny robot that essentially is learning how to walk. And again, the whole paradigm is about learning from experiences. In this case, the robot is learning how to walk. The model that is in this robot, that is instructing it on what is the path to take, what are the different actions, how to control the motor, how to control the joint and all these things, that's a model that was already learned. And that's a model that was learned through multiple iterations of estimation and control and experiences essentially in potentially a simulator. So what essentially I'm trying to convey here is this big relationship between the simulation environment that can help you at a massive scale to run multiple hundreds of thousands of experiments and then bring the best performing experiment algorithm into a physical environment, like in this case a robot, and have that robot carry out a certain action in real life. And if you bring it back to the conversation that we had on the business goals for machine learning and AI, if you think about acting, if you think about exploring, and if you think about predicting, what I predict is that you will see more and more applications of even traditional AI problems, like finding out if a claim would be accepted or not, coming from experiments that were run in a simulator at a massive scale, and then 10 years of experience AI model by basically simulating 10 years in a simulator would be deployed in that environment and would be able to handle some variability into the ecosystem in which that model lives. So we're seeing a lot of simulation coming back into the world of AI, and arguably it's a very big challenge nowadays to kind of figure out what that entire architecture looks like. Because in the big data world and in the machine learning, traditional machine learning work, we know what to do. We have the data lake, we load the data into the data lake, and then we train the machine learning model, we get the model, we deploy that in the real world. But if you have to do with simulation, generate data in the simulation, at which point do you bring it back to a machine learning model, and how do you interconnect these two ecosystems to make sure that they work together? So what we've done to kind of simplify that process is we've created this fun machine, or this little toy car, which is called the AWS Deep Racer, that you might have seen at the Deep Racer ecosystem there, which is basically a fully autonomous 1/18th the scale of a normal car, and it's driven, or it's powered by reinforcement learning. Again, that's our approach to make sure that you can play with a lot of estimation and control and reinforcement learning problems on your own, and then learn that entire end-to-end architecture, and again, apply that to all sorts of use cases that you might want to apply that to. And basically what Deep Racer looks like is a tiny car that has an HD video camera for perception problems, and then you can complement the perception problems or define the entire perception capability with things like an accelerometer and a gyroscope as well to find out exactly what is the heading of a car, and an accelerometer to find out at which speed the car is going. So all of that combined with a camera can essentially tell you where you are. It has two power banks, essentially, one for the drive and then one for compute. And it has a dual-core Intel processor, four-wheel drive, and so on and so forth. So it's a really powerful tool. And just to break that open a little more, I just like this video because it's funny. So it has, again, like I said, about 4 USB A plugs. It has one USB-C plug and then one micro USB plug. Essentially, it's a really dismountable toy that you can break open and then play with. It has an Ubuntu operating system in it with a Rust Kinetic toolkit in it, so you can basically run your simulated environment or your simulated code or simulated model into this little toy and get to solve some problems with it. So, and then the way it looks like, essentially the call out that I want to bring forward here is not just the reinforcement learning piece, but it's the relationship between the simulated reinforcement learning environment and the traditional machine learning environment. So what I spoke about earlier is Amazon SageMaker. In Amazon SageMaker, we released this reinforcement learning capability, which is basically us packaging the brain of reinforcement learning, the ability to run a reinforcement learning experiment and then train a policy or train a reward function or anything like that in the reinforcement learning ecosystem if you're familiar with these algorithms. So it supports the Intel Coach platform or framework for reinforcement learning, or the Ray library for reinforcement learning. We have all that in there. But to see that in action with the simulation environment that we have called Amazon RoboMaker, this is practically how it would work in the case of a self-driving car. So you would have trained the brain in Amazon SageMaker, in this case using a proximal policy optimization, and then the action is handed over to the simulated environment or to the simulator, in this case Amazon RoboMaker. And based on the action, eventually, the car is going to take based on the action that is proposed by the brain, the car is going to take a certain step. And after the step is taken, the reward is gathered by their experience within the simulator. And that's basically the data set generation ecosystem or mechanism. I'm pretty sure many of you are familiar with reinforcement learning. That's not the goal of this exercise. The goal is to show the relationship between the two tools. And eventually, what you want is through these iterations and interactions between the brain and the simulator, you want to find the best possible policy. And the policy in this case is the shortest path to the goal that is there. So by doing that, by running the experiments within the simulator and gathering the data and handing that over to SageMaker to kind of search for the best policy within the SageMaker ecosystem, you're having two tools, one fundamental machine learning, deep learning platform working seamlessly with one fundamental robotics and then simulation platform, and for the purpose or for the ultimate goal of finding the shortest path to getting the car to the goal, right? So that's kind of what we're doing there. And to take a step back and basically talk about what we do in this ecosystem, we integrate these two tools and we make sure that they work well together. So again, the Deep Racer is a toy example to show how to integrate these two ecosystems, but you can totally do that for your claims processing example or for your other examples. And at the end of the day, once the model is figured out, you can basically pull that out into the real world. So in this case, I represent that by a car, but you could also deploy that in your web application or on the SageMaker backend ecosystem. So again, we're seeing a lot of innovation on the adoption of this paradigm where you have a reference architecture of a deep learning platform working with a simulation platform together in order to train an AI that learns from experiments as opposed to learning from data that was gathered up front. And so some of the examples, there's a lot of examples out there in the market. So robotics is very obvious. A lot of the talks here are talking about robotics in relation with reinforcement learning. Autonomous vehicles, one of my favorites. But again, finance, you heard about simulating financial markets. Things like industrial control and HVAC and so on and so forth. But my argument is that it's applicable everywhere. If you have a system that generates data and you can gather that data into some kind of environment, then you can run these experiments and search for the best policy of the behavior of your model as opposed to training the model to take some actions based on pattern recognition. Okay, so just for closing with that, so if you think about how do we get started, I want to bring it back to the three major points that we called out earlier. It all starts with the data. It all begins with the data. You heard Adam saying that one of the gates of getting started with a machine learning project at Change Healthcare is to ask yourself whether you have the right data set. And then to ask yourself whether you have access to that data set, do that little investment up front into finding out what is your data lake strategy, organize the data cataloging, organize the growth plan of your data set, because as data grows, you're going to fall into issues in terms of the control of that data set and so on and so forth. So have a data strategy, very important. Everything, if you don't have organized data, you have nothing. And the second thing is that leverage the platform as much as you can for AI-driven development. Again, Adam shared that in his team, it's not data scientists on one side, developers on one side, and DevOps people on one side. It's an entire hybrid team that is working together in an interdisciplinary manner and basically takes one problem and works end-to-end to solve that problem. And we've designed Amazon SageMaker to follow the developers and the data scientists through that pattern and make sure that the tools are interconnected in a way that enables AI-driven development. And the third major call out, again, is take advantage of the new paradigms. Big data is massively important. I spent 3 years of my initial life at Amazon running a big data engineering team, so I'm a big fan of the big data ecosystem. But one of the things that I'm observing right now is that we're moving into the ability to learn from experiments as opposed to learning from data set that is sitting somewhere, because it's hard to find clean data set that is sitting somewhere. But we can find the opportunity to learn from experiments. So think about estimation, think about control, and then we have that capability in SageMaker reinforcement learning today. So with that, thank you. Thanks for your time. And you can find more at ml.aws. Thank you.